Imagine building a massive bridge, pressure vessel, or power plant pipeline. Now imagine a single tiny weld crack bringing everything down. Scary, right? That's the power of weld quality. In today's video, you will learn how to inspect welds properly, the most important weld testing methods, how to identify weld defects, and the correct way to rectify faulty welds. Whether you're a student, engineer, inspector, or welder, this video will upgrade your skill level. Let's begin. Welding joins metals permanently, but a bad weld can cause equipment failure, leakage, cracks, explosion risk, and even structural collapse. That's why weld inspection is done to ensure strength, safety, durability, and compliance with standards. Weld inspection happens at 3 stages: before welding, during welding, and after welding. Visual inspection is the simplest and most common method. The inspector checks for cracks, porosity, undercut, overlap, lack of fusion, excess reinforcement, spatter, and surface finish. Tools used include a welding gauge, torch, measuring scale, and a magnifying lens. If the surface itself fails inspection, further testing is done. These non-destructive tests check internal and surface defects without damaging the weld. First, the dye penetrant test, or DPT, is used for surface cracks. The process involves cleaning the weld, applying penetrant liquid, letting it seep, removing excess, and then applying developer powder. Cracks become visible as red lines. Next, the magnetic particle test, or MPT, is only for ferromagnetic materials like carbon steel. Cracks disturb the magnetic field, causing iron particles to gather, making the defect visible. Ultrasonic testing, or UT, uses sound waves. When sound hits a defect, echoes return, and the signal shows on a screen. This detects internal cracks, lack of fusion, and inclusions. Radiographic testing, RT or X-ray, uses X-ray or gamma rays. It's used in pressure vessels, pipelines, boilers, and structural welds. This method shows internal defects like porosity, cracks, and slag inclusion. Finally, eddy current testing is common in aerospace and high-precision industries, detecting surface defects in conductive metals. Now, let's talk about destructive testing, where the weld is broken to check its real strength. The tensile test pulls the weld until it breaks, showing tensile strength and ductility. The bend test involves bending the weld. If cracks appear, the weld fails. The hardness test checks the heat-affected zone, as too hard means brittle and too soft means weak. The impact test measures toughness, especially important in pressure vessels and structures. Let's identify major weld problems. Porosity, caused by gas trapped inside the weld. Cracks, due to rapid cooling, wrong electrodes, or hydrogen embrittlement. Lack of fusion, from wrong heat or incorrect technique. Slag inclusion, where flux gets trapped inside. Undercut, a groove at the weld toe. And spatter, metal droplets scattered around the weld. Repair process depends on defect type. First, confirmation. Verify the defect by NDT. Next, defect removal using methods like grinding, gouging, or chipping. Then, rewelding with proper WPS, controlled heat, and correct filler material. Finally, reinspection. Repeat testing until the weld passes, meets standards, and is safe to use. A strong structure starts with a strong weld. Inspection, testing, and rectification lead to reliability, safety, and longevity. Never ignore defects. Remember, a small crack today can cause a big failure tomorrow. If you found this useful, like this video, subscribe to SimpleGAN, comment your doubts, and share with engineers and welders.